Hey everyone, and welcome back to The Explainer. I am so thrilled you're joining me for this GeoVault 77 Deep Time Earth Science deep dive into the Andes, South America's backbone of fire and gold. Today, we're taking a look at quite literally Earth's most massive geological engine. We're talking about a place where immense planetary forces collide, where liquid rock builds the sky, and where our deep time past holds the absolute key to our high-tech future.
Picture this. The longest continental mountain range on Earth runs a staggering 7,000 kilometers down the western edge of South America. And the crazy thing? It is still growing. Right now, one earthquake at a time. We're talking, of course, about the mighty Andes. You see, this isn't just some static, ancient pile of rocks. This is an active, violent, and incredibly beautiful construction site. It's a mountain range built by an entire ocean literally being eaten by a continent. It hosts the world's largest copper deposits, it shapes the driest desert on the planet, and it's happening right beneath our feet.
So, here's our roadmap for today. We're going to break this incredibly complex system down into 4 clear chapters. First up, we'll look at the sheer scale of the Andes. Second, we're going to dive underground to uncover that tectonic engine, the ocean being eaten. Third, we'll resurface to see the explosive results of a range built by fire. And finally, we'll connect all of this deep-time geology directly to our modern power grid by looking into the world's copper vault.
All right, let's jump right into Chapter 1, the longest mountain range on Earth, scaling the continental spine. Let's just try to wrap our heads around the massive scale of this thing.
To put this into perspective, think about the planet's other great mountain ranges. The differences are staggering. The Himalayas, they're about 2,400 kilometers long, boasting incredible peaks like Everest at 8,849 meters. The Rockies span roughly 4,800 kilometers. But the Andes, they stretch an unbelievable 7,000 kilometers from Venezuela all the way down to Tierra del Fuego. They pass through 7 different countries, with peaks like Aconcagua reaching an immense 6,961 meters. In fact, literally the only thing longer is the underwater mid-ocean ridge system. But here's the absolute most crucial point: the mechanism. The Himalayas are built by continents colliding, right? India smashing into Asia. But the Andes are completely different. They are built by subduction, an oceanic plate diving under a continental plate. And that is exactly why the Himalayas have 0 active volcanoes, while the Andes have well over 50.
Now, here's a wild geological paradox for you. The Himalayas have actually experienced 2 to 3 times more tectonic shortening. What that means is the continents there squeezed together far more intensely than South America has been squeezed. And yet, the physical volume of the central Andes is roughly twice as large as the Himalayas. How on earth is that possible? Well, it all comes down to climate. The Himalayas get absolutely battered by the intense Indian monsoon, which erodes the mountains incredibly fast, just washing all that rock away as sediment. The Andes, on the other hand, act as this massive weather shield, creating the hyper-arid Atacama Desert. Because it rarely ever rains, the mountains simply don't erode as fast. They just keep stacking up and up and up.
Which brings us to Chapter 2, the Nazca Plate, an ocean being eaten, uncovering the tectonic engine. We've seen the surface, but now we need to look under the hood at the massive engine driving it all.
Okay, 2 quick terms we need to nail down to really understand the Andes. First, a subduction zone. Think of this as the crunch point where a heavy, dense oceanic plate is literally forced underneath a lighter, more buoyant continental plate. Second, the Nazca Plate. This is the specific piece of Pacific oceanic crust born way out at the East Pacific Rise that is currently plunging eastward beneath South America at a staggering rate of 7 to 8 centimeters per year. Geologically speaking, that convergence rate is an absolute sprint.
So as that dense Nazca Plate dives down into the superhot mantle, it heats up and actually sweats out water. This water rises up into the mantle wedge right above it. Now, if you add water to hot mantle rock, it lowers the melting point, causing that solid rock to melt into magma. This buoyant, fiery magma then rises up through the incredibly thick South American crust, eventually erupting at the surface to create the whole Andean volcanic arc. And at the exact same time, all this intense friction and heat is compressing and thickening the continental crust, physically jacking the mountains higher into the sky.
But, nature rarely runs in a perfectly straight line, and this engine doesn't always run smoothly. Normally, subduction is steep. The plate dives deep, it melts, and creates a neat, orderly line of volcanoes. But sometimes, the diving oceanic plate has a buoyant ridge on it, maybe an underwater mountain chain or a cluster of seamounts. When that happens, it acts kind of like a life jacket. It refuses to sink steeply, forcing what geologists call flat slab subduction. The plate just scrapes horizontally right up against the bottom of the continent. This immense friction transfers compression really far inland, widening the whole mountain range. And because the plate doesn't dive deep enough to melt, it temporarily shuts off the magma engine above it, creating a very noticeable gap in the volcanic chain.
Moving right along to Chapter 3, a mountain range built by fire. The volatile surface. Let's head back up to the surface and look at the fiery, immediate consequences of this tectonic engine.
Because of those flat slab sections we just talked about acting like a wedge, the Andes actually aren't just one solid, continuous wall of fire. They're broken up into 4 distinct volcanic zones, completely separated by amagmatic gaps where no volcanoes exist at all. You've got the northern zone up in Colombia and Ecuador, the central zone spanning southern Peru to northern Chile, the southern zone in central Chile, and the austral zone all the way down in southern Patagonia. And each of these segments has its own entirely unique geological flavor, based on the exact angle of the dive, the age of the slab, and whether there are underwater seamounts getting dragged down beneath it. They're basically a giant stack of distinct geological provinces.
And we are talking about some absolute explosive giants here. Think about Ojos del Salado on the Chile-Argentina border. At 6,893 meters, it is literally the highest active volcano in the entire world. Then there's Cotopaxi in Ecuador, towering beautifully but super dangerously over the landscape at 5,897 meters. We also have Nevado del Ruiz in Colombia, which is a really stark, tragic reminder of the volatile nature of this region following the 1985 Armero disaster. And of course, Villarrica in Chile, one of the most consistently active and fiery mountains on the continent today. This is the raw, unfiltered power of the Nazca Plate venting directly to the surface.
Finally, Chapter 4, the world's copper vault. Deep time geology meets the modern grid. Because this is where the story of the Andes directly impacts your life, right now, as you watch this explainer.
This brings us to a term that literally powers our modern world, porphyry copper. These are massive, economically absolutely crucial deposits of copper, molybdenum, gold, and silver that form in shallow magma chambers right above these subduction zones. And the Andean subduction margin is the ultimate textbook example. It has been perfectly, relentlessly manufacturing these deposits for over 40 million years.
So, how exactly does a mountain range manufacture copper? Well, it's like an incredible 4-step chemical recipe. Remember how subduction physically thickens the crust? Well, step 1, the crust has to get immensely thick, over 45 kilometers thick. When magma has to travel through crust that deep, step 2 kicks in. Extreme pressure causes a specific mineral called garnet to crystallize. And garnet acts like a giant sponge for iron. It sucks the iron right out of the magma, but it leaves all the copper behind. Step 3, without that iron, the magma fundamentally changes its chemistry. It basically auto-oxidizes. And finally, step 4, this highly oxidized state allows super hot hydrothermal fluids to literally scavenge all the tiny, microscopic bits of copper spread throughout that massive magma chamber, sweep it all up and concentrate it into one small, highly enriched zone at the top. Boom. The Andes are basically the world's ultimate copper refining machine.
And this incredibly specific chemical process leaves a massive, massive footprint. The legendary mining giants cluster right along the thickest parts of the ancient magmatic arc. We are talking about places like Chuquicamata, which was the world's largest open-pit copper mine for most of the 20th century, and Escondida, which today produces over 1 million tons of copper a year, all by itself. No way, right? They're joined by other massive deposits like Collahuasi, Los Brances, and El Teniente in Chile, plus major silver and gold producers like Peru's Cerro de Pasco and Yanacocha. To truly grasp the sheer scale of this, get this, global breakdown. Thanks entirely to this very specific subduction geometry, that incredibly thick crust, and that whole garnet-driven chemistry recipe we just explored, Chile alone produces nearly 30% of the entire world's copper. Let that sink in. One single nation, riding on the back of one single tectonic boundary, supplies almost a third of the foundational metal required for all of modern human civilization. So think about the device you're using right now to watch this explainer. Think about electric vehicles, our power grids, the wind turbines, this entire modern energy transition we're going through. Absolutely all of it relies on copper. So it really makes you wonder, without the relentless, ocean-eating, deep-time tectonic engine of the Andes grinding away over millions and millions of years, would our global electronics industry even be possible? It's just a profound reminder that human history and honestly our entire technological future are completely bound by the ancient, ongoing geological forces of our planet. Thanks so much for joining me on this journey. Keep asking those big questions, and I'll see you in the next explainer.